In this lesson, we're going to solve a system of linear equations in 3 variables. This is section 5.2. So a linear equation in 3 variables has this form. We did previously have a system with 2 variables where we had just ax plus by equals c, but now notice that we have another term, a variable term, with z. So this is the new general form with 3 variables. And we're told that a, b, c, and d are real numbers and not all 0. So the solution is not an ordered pair, but an ordered triple, and it's written in the XYZ form. And it actually represents the intersection of 3 planes in space. And here's a graphical representation of 3 planes in space intersecting at that ordered triple, XYZ. One of our objectives is to determine if a given ordered triple is a solution to a system of linear equations in 3 variables. And so we have to plug in all 3 variables into each equation, and that ordered triple must satisfy each equation. So for example 1, determine if the ordered triple 5, -3, -2 is a solution to this system of 3 equations. This is x, this is y, and this is z. So taking one equation one at a time and evaluating at these values, we'll see if this ordered triple satisfies all 3 equations. So taking the top equation, I'm just going to put a little line through my z. So if x is 5, y is -3, and z is -2, does that question mark equal 0? While doing all this work on my calculator, I do get 0 equals 0. So far, so good. I have 2 more equations to check with this ordered triple. I'm grabbing the middle equation. Those will cancel, so yes, 5 equals 5. Two down, 1 to go. Let's see if the given ordered triple satisfies this last equation. Yes, -1 equals -1. So that's just strictly calculator work. So let's respond. Yes, 5, -3, -2 is a solution. All right, so the bulk of our work is going to be to solve a system of linear equations in 3 variables. And these are the steps that we're going to be using to solve a system of 3 equations in 3 variables. So we're going to reduce the system to 2 equations and 2 variables by taking 2 equations at a time. Once we get 2 equations with 2 variables, we have practice with solving that type of situation. We could either use the substitution or the elimination method. So step 2 says once we reduce this system of 3 equations to 2 equations, we can solve the system of 2 equations using either elimination or substitution. And then we just go back, substitute values to solve for the remaining 2 variables. We're going to express our solution as an ordered triple, and we're going to check our solution. All right, looking at example 2, we've got this system of linear equations in 3 variables. So I have 3 equations and 3 different variables, x, y, and z. All right, the first step is we want to decide which variable do we want to eliminate. Do we want to eliminate all the x's? Do we want to eliminate the y's? Or do we want to eliminate the z's to get to just 2 variables? Well, for me, when I look at trying to use this strategy, I look at all the terms individually. So, for example, I might look at all the x terms, and I look at the coefficients mainly. So I see a coefficient here is 1, 3, and then I have 2. I'm looking for a coefficient of 1 or -1 to help my work be a little bit easier. And you'll see why in a minute. So it's a possibility that I might want to eliminate some x's and only have an equations with y and z, because I see a 1 here. Let's just kind of look and inspect the y terms. Notice that all the y terms have coefficients that are not 1 or -1. So, I mean, I might work with the y's to eliminate the y's, but probably not. Okay, look at the z terms. I see that in the top equation, this coefficient is -1. In the middle equation, this coefficient is 1. And then we have a 2 coefficient here. I'm probably going to want to eliminate z's, just because I look for the terms that have coefficients of 1 or -1. And in 2 equations, I have either 1 or -1 in front of the z's. So I'm just going to put a note over here to myself that I'm going to eliminate z. Will it matter at the end of the day if I had chosen to eliminate x's or y's? No. If we do all the work correctly, we should get the same ordered triple. All right, so coming over here, notice I kind of got it started. I said, okay, let's go ahead and pair the first and second equation together, the top and the middle one. So I'm going to just go ahead and rewrite those 2 equations over here. You might not see yet what we're doing, but it'll be revealed. Okay, so what I'm going to do is I'm going to pair the first and the second equation because my choice is to eliminate the z's. So I notice that the coefficient on the z's are the opposite of each other. So if I put my straight line here, it means I'm ready to add down. That when I do add down, my z's will be eliminated using equation 1 and 2. So collecting down, I'm going to get 4x plus 6y equals 28. Okay, this is going to stay on hold for just a minute. Now what we need to do is we need to grab 2 more equations, not the first and second again, but any other combination. And we're going to grab 2 different equations and we're going to eliminate the z's in those 2 equations. So let's look at the second and third equations. So I'm going to rewrite those. Okay, before I draw a straight line here, which to me indicates I'm about to add down, I'm going to make sure that when I do add down, I have the z terms are going to eliminate. Well, when I kind of quickly inspect, when I add down here, I'm not going to eliminate the z's, which is what I want to do. I'm actually going to get 3z if I were to add. So at this point, how would I eliminate these z's? Well, if you multiply the top equation by -2, -2 multiplied by z would give you an opportunity when you add down to cancel the z's here. I don't need to make any equations in this, I don't need to make any changes in this bottom equation here because I will be able to add down and cancel the z's by only multiplying the top equation by -2. So instead of drawing a straight line, not anything mathematical, but just indication to me, I am not ready to add down yet. I still have to do some multiplication in order for me to be able to add down. So at this point, I'm probably gonna, let's see, how do I want to do this? I'm gonna kind of come over this way. Let me multiply the top equation by -2. And don't forget, it's not 8, it's -16. Then I'm gonna re-record the bottom equation that I'm not making any changes to. Just be careful, all these numbers and variables, a lot of opportunity for mistakes. You see how I made that straight line? That means that I'm ready to add down because I'm going to be able to cancel the z terms. Again, it's not a mathematical thing. It just kind of tells me where I'm at in the problem. Now let's add down. Okay, so now what we notice is going back over here, I have the equation 4x plus 6y equals 28. And I have this equation, -4x minus 7y equals -32. Now I'm going to put these 2 equations together and solve the way I did in the previous lesson. So right here, 2 equations and 2 variables. Let's re-record those 2 equations. Okay, now I'm going to stop and inspect my new set of equations here and go, okay, do I need to make changes to any one or possibly both of these equations so I can eliminate one of the variables? Well, as you can see, when you look at the x terms, the coefficients are already opposites. I don't need to multiply either one of these equations by a constant multiplier to eliminate one of the remaining variables. So draw a straight line, you're ready to add down. And when we do, we're going to get just -1y equals -4. Divide both sides by -1, and we get positive y equals positive 4. So at this point, we have one of the three of our values that we need. Now we just need to find x and z. So what do we do here? We got to plug 4 into one of our previous two equations. So either using this top equation or this bottom equation, since we do have y equals 4, we're going to be able to solve for x. And once we get x, then we can plug that value for x and this value for y into one of the original equations to get the remaining z value. All right, I got y equals 4, so it doesn't matter. I'll just use the top equation. Let me re-record it here. Okay, y is 4, and we'll solve for x. All right, x is 1. Okay, so now all we have to do is find z. So that's going to take us back to the original equations. It doesn't matter which one you use. I guess I'll just use the top equation. All right, we know x's value is 1. We know y's value is 4. This is 16. So 16 plus 1 is 17. I'm going to subtract a 17. Don't forget to bring that subtraction down as a negative, so negative z equals 3. Divide both sides by -1. And I will end up with z equals -3. So trying to find a space here. Let's record our answers in ordered triple. X comes first, then y, then z. And this is the solution to our system of linear equations in 3 variables. Oh, goodness. Let's just practice again. Okay, kind of ignoring this information right here. Let's see if we can figure out which variable we want to eliminate. So inspect your equations. The x terms have coefficients of 2, 3, -1. That's a possibility. The y terms have coefficients of 1, -3, -2, and the z coefficients are -2, -1, and 3. It looks like in all of the variables x, y, and z, I have at least one coefficient that's 1 or -1. So at this point, it doesn't matter. You can choose what variable to eliminate. Just for the sake of being something different from the last example, let's eliminate the y's. Again, it doesn't matter. You could have eliminated the x's or the z's, just like in the last example, but just to mix it up, let's eliminate the y terms. So what I want to do is kind of figure out which equation I want to work with. I'm probably going to work with equation 1 and equation 2, put these together, because to eliminate the y's, if I put these two equations together, I would multiply the top equation by 3 so that I could do that. And then I'm probably going to pair the top equation with the bottom equation so that to eliminate the y's, I would just multiply the top equation by 2. So I'm going to pair equations 1 and 2, and then 1 and 3. So I have it set up 1 and 2 and 1 and 3. So let's re-record equations 1 and 2. Okay, I'm going to eliminate the y's. So I do have to multiply this top equation by 3 to get 3y to eliminate with -3y. So I'm going to do this little squiggle because I'm not ready to add down. Okay, right down below here, I'm going to go ahead and distribute the 3 in. And then re-record the bottom equation that you're not making changes on. Let's be careful. It's easy to make little math mistakes and also transcription errors when you copy things over. All right, eyeballing the y terms, they will eliminate, so I'm going to draw my straight line here, not squiggle. collecting down. This equation is on hold while I try and eliminate the y's in another set of equations. So first and third, let's re-record those. All right, our target is to eliminate the y's. Let's multiply the top equation by 2. Little squiggle. Let's distribute. And re-record the bottom equation. Straight line, because we are going to eliminate the y's. Let's add down. Okay, now we have 2 equations with 2 variables, x and z. So let's put these together and just solve from our previous knowledge. All right, so what should we eliminate, x's or z's? Well, if you eliminate the x's, then you're going to have to multiply the top and bottom equation by a different number so that you can eliminate these. But I'll try and work with this coefficient of -1 here. I want to make this a positive 7x here so that when I collect with positive 7z, so when I collect with negative 7z, they cancel. So I'm going to take the bottom equation and I'm going to actually multiply the bottom equation by -7. So squiggle line, re-record the top equation, distributing -7 to the bottom equation. Now these 2 terms will eliminate. Straight line. Be careful here, just use your calculator. That's going to be a -26x. Cancels. These collect to -26. Divide by -26. So actually this works out to be a nice number, and that's +1. If you get some weird decimal here, chances are that you made a mistake somewhere. Maybe you forgot to distribute this constant multiplier into this answer right here. So just go back and check your work. All right, let's back substitute. So we've got x equals 1. Don't go to the original equations yet. You're not ready. Let's plug 1 in for either this equation or this equation right here. It doesn't matter. I'll just choose the first equation. So when x is 1, let me subtract a 9. Use your calculator. That's -7. Divide both sides by -7. So z is +1 again. So x and z are both 1. Let's find y. So choose one of the equations in the original problem. X is 1. We're solving for y. Z is 1. And actually these 2's will eliminate, so y is -1. So our ordered triple, x, y, z, is 1, -1, 1. Not too complicated, just kind of tedious. All right. So we're going to look at an application problem. All right, so we're not given the equations. We have to actually create them. So we want to define our x, y, and z variables first. So the sum of 3 numbers is 16. So let's let x be the first number, etc. y is the second number, and z will be the third number. We're adding three different numbers together. So x is first number, y second, and z is the third number. Got it. All right, let's go back to the problem and kind of decode, see if we can come up with the three equations that we're going to be solving. So the sum of three numbers is 16. Well, that looks like just x plus y plus z equals 16. One down, two equations to create. The sum of twice the first number, so 2 times the first number, plus, for the sum, 3 times the second number, 3 times y, and 4 times the third number, 4z, is 46. All right, let's see what this last sentence says. The difference, so we're going to subtract, the difference between 5 times the first number, so 5 times the first number, subtracted by the second number is 30. Okay, so we're going to take 5 times the first number and subtract just the second number, and that difference is equal to 31. So notice in the third equation that we don't even have a z representation. That's actually a little gift to us. That's going to help us. If I don't have a z here, then let me eliminate the z in equation 1 and 2. So I have a little less work if I'm missing one of the variables. All right, so equation 3 doesn't have a z in it, so that tells me that I'm probably going to take equations 1 and 2 and eliminate the z term. So let's come over here. I'm just going to tell myself that I'm grabbing equations 1 and 2, the first and second equations, and I'll re-record them over here. Okay, remember what we're going to do, sorry about that, is we're going to eliminate the z. So to eliminate the z terms, I'm going to have to multiply the top equation by -4 so I can eliminate with this 4z here. So just put a little note to myself here. I'm multiplying by -4. I put the -4 over here instead of up here because I'm running out of room. So let's distribute that through. Okay, so remember my little squiggle means I'm not ready to add down. So I'll multiply the top equation by -4. Okay, now I'm ready to add down. Collecting down here, -2x. Collecting these two terms gives us -1y. Those eliminate, and use your calculator here, and I believe you're going to get -18. Are we done? No. But what we do have is we have these two equations that just have an x and a y in them. We'll put them together. We'll use the elimination method and continue solving for our answers. Are we ready to eliminate the x's or y's? No, not yet. We've got to get one of these to be a positive y. So I'm just going to multiply the top equation by -1. That'll change that to +y, and it'll change this sign to -31. And just re-record this below here. Just be careful. Double check it, look back, make sure you didn't make any transcription errors. Straight line, add down, -7x. Those are eliminated. Ooh, that's -49. Divide by -7. X equals +7. All right, so what should we find next? Well, I'm going to find y next, not z, because I have these two equations right here. Okay, they just have x's and y's in them. I'll just use this top equation right here to find y. Divide both sides by -1. The result is y equals +4. All right, running out of some room here, but now I have x and y, and all I need to do is find z. So let's go back to the original equations here. To find z, I'm either going to have to use equation 1 or 2. I'm going to go ahead and use equation 1. So I've got a little squiggle here to kind of separate my work. So x plus y plus z equals 16. X is 7, y is 4. So this will be 11. I'm going to come back up here. 11 plus z equals 16. Subtract your 11. All right, and let's finish by putting our answer in an ordered triple form. So I'm going to come up here. I have a little more room. What was x? 7. What was y? 4. And z was 5. Okay. And then at this point, I would probably just tell you that I think what we're going to do on this one is we're just going to set up the equations. We're not going to actually solve them. I hope that you feel comfortable with solving a system of linear equations with 3 variables. I think the challenge here is just going to be setting up the equations that represent the information given here. So maybe kind of read through this problem. We'll define our variables, we'll set up our equations, and we'll stop there and not solve. My worked out solutions do have the key. If you want to, self-assess and see where you're at, you can certainly work it out and check the key that's online. But take a moment and just read through the problem. All right, so we've got razor blades we're talking about, and we have razor blades in packages of 6, 12, and 24. So let's come over here and define our variables. Let's let x, the variable x, represent the number of packages of 6. Y will be the number of packages of 12, and then you see what z is going to be. All right, so x is the number of packages of 6, y is the number of packages of 12, and z is the number of packages of 24 that Walgreens, CVS, whatever sells. All right, so a certain brand of razor blades comes in packages of 6, 12, and 24 blades. Got it. Costing $2, $3, $4 respectively. Okay, CVS, Walgreens, whatever, store sold 12 packages. We don't know if it was packages of 6, 12, or 24, but we know that the cashier at Walgreens checked out, people that in a total of 12 packages were sold. So a store sold 12 packages. Well, I'm going to take and let that be my first equation. The number of packages of 6 plus the number of packages of 12 plus the number of packages of 24 had to equal 12. All right, so we had a total of 162 razor blades. All right, so in all those packages, if you added up all the razor blades, there were 162 of them. Well, in one package of 6, if I wanted to figure out how many razor blades that were, I'm going to take 6 and multiply it by x. Y represents the number of packages of 12, so let's multiply 12 in each of those packages, and then 24 times z. All right. So what else is in this information that's going to help us get a third equation? So CVS, Walgreens, whatever, took in $35. So, and we know the cost of each of these different packages. So they took in $35. This is our cost equation. So for every package of 6 that they sold, they made $2. For every package of 12 of razor blades they sold, they made $3. And then they made $4 for every package of 24. Okay, it takes a little time to kind of, come up with these equations. I sometimes I have to read the problem over and over again, but I'm thinking that we've got the equations that we need. And then the next step is just to find how many packages of each type of razor blades were sold by using our strategies that we just had a few examples of. So, and I'll leave that for you if you're interested in solving it, if you need a little more extra practice.